Hey everyone, welcome back from a rather unusual spring break. This is the unit we were working on before spring break. It was Unit 5, Rational, Radical, Absolute Value Expressions and Equations. And so far we've actually done this first one, Rational Expressions. This was Lesson 1A. And then we did Solving Rational Equations. That was Lesson 1B. Today we are going to do Radical Expressions. This is Lesson 2B. 2A. And then later on, hopefully, we will get to Lesson 2B here, which is Solving Radical Equations. And then there's no longer A and B. This will be Lesson 3, and so on. Okay, so for today, we are on Lesson 2A, which is Radical Expressions. These notes are posted on my website, so you can print off the notes and then follow along and fill them in. I'm going to call mine answer key. And it goes like this. A radical expression is one that contains the square root sign. And the first thing we're going to look at is simplifying radicals. Simplifying radicals involves dividing out what are called perfect square factors. Perfect squares are numbers whose square root is a whole number. Some common perfect squares are 0, because the square root of 0 is 0. 1, because the square root of 1 is 1. 4, because the square root of 4 is 2, and so on. The square root of 9 is 3. The next one is 16. Square root of 16 is 4. And then we would have 25, and 36, and 49, and 64, and 81. And I'm actually going to do a few more. The next perfect square is 100. And then 121. 12 times 12 is 144, so the square root of 144 is 12. 13 times 13 is 169. 14 times 14 is 196. And 15 times 15 is 225. Okay, and they continue in this manner. Okay. And so in order to simplify radicals, what we can do is try to divide out one of these perfect square factors. And the reason you do that is because these perfect squares have nice square roots. And so, for example, convert each entire radical to a mixed radical in simplest form, the square root of 48. We want to try to divide from 48 one of the perfect squares in the list above. Okay, now first thing I should say is we can't divide by 0, so I'm never going to divide by 0. And if I were to divide 1 out of 48, that wouldn't change the 48, so there's no point in looking at those two. So imagine if we went the square root of 48 times the square root of 1, it doesn't change the root 48. So that's why we're not going to divide by 1. Okay, so we want to find a number on the list above here that goes into 48. And usually, guys, it's good to try to find the biggest number that you can that goes into 48 in this case. So 48 lands right in here, in between 36 and 49. So we're not going to try anything that's larger than 48. We would start with 36. 36 doesn't go into 48. 25 doesn't go into 48, but 16 does. And so you can write the square root of 48 as the square root of 16 times the square root of 3, because it's 16 times 3 that equals 48. And then from there, the square root of 16 is a nice number, 4. The square root of 3 is a not so nice number, and so we're going to leave it as the square root of 3. So if you look at the square root of 3, it is this 1.73, and it continues forever and doesn't repeat. It's called an irrational number. So you put 4 and you put the root 3 beside it. That means 4 times root 3. And that is what we call simplest radical form. Okay, because you'll notice that the 3 doesn't have any perfect square factors. 3 lands right in here. It's less than 4. So none of the perfect squares will go into it. All right, let's try the square root of 27. Now 27 lands in here, so we would try dividing it by 25. That doesn't work. Divide 27 by 16, that doesn't work, but 9 is the one. This is the square root of 9 times the square root of 3. And the square root of 9 is 3, so that simplifies to 3 root 3. In example 3, we need to find a perfect square that divides into 200. The answer is actually 100. I mean, 200 lands here, right? So you could look at all of those individually. 196, 169, 144, and 121, but we know that those aren't going to divide in evenly. It's the square root of 100, and it's 100 times 2 that's equal to 200. The square root of 100 is 10. Root 2 cannot be simplified anymore, so the answer is 10 root 2. All right, and so that is converting what are called entire radicals to mixed radicals. A mixed radical is of the form a times root b. And an entire radical is just the square root of something. Example 2, convert each mixed radical to an entire radical. So this is going backwards now. And so what we need to do to write this as an entire radical is you have to write the 3 as the square root of something. So I have to say, okay, 3 is the square root of what? Well, it's the square root of 9. Okay, and so we can write this as, instead of 3 times root 5, it's the square root of 9 times the square root of 5, which is root 45. Okay. Once you have the square root of something times the square root of something else, you can multiply the numbers inside. Okay, and letter B here, 2 root 6, we'd have to say 2 is the square root of what? Well, it's the square root of 4, and then we're multiplying by root 6. 2 roots multiplied together, we can multiply the insides. 4 times 6 is 24, and we're done. That's an entire radical. And the last one, 4 can be written as the square root of 16. Root 16 times root 7, you just go 16 times 7, and we can put that under a square root. It's the square root of 112. Okay, so then we can get on to adding and subtracting radicals, and when adding or subtracting radicals, we can only add or subtract like radicals. Okay, it's kind of like adding and subtracting like terms. Remember how you can only add x's with x's and y's with y's? Okay, so we can only add or subtract like radicals. That is, radicals that have the same square root part. This is similar to adding like terms in algebra. As formulas, the properties look like this. If you have a root c plus b root c, you can add the numbers in front and put that in front of root c. Similarly with subtraction, a root c minus b root c, you subtract sort of the coefficients, you subtract the a minus b and put that in front of root c. So if we look at example 3, simplify each of the following expressions. If I have 3 root 3's and I add 3 root 5's and I add 5 root 5's, my answer is 8 root 5's. You add the numbers out front. It's kind of like having 3x plus 5x equals 8x. It's similar to that. All right, so in example B, notice we've got root 6's and we have root 3's. Okay, so we have to add or subtract the root 6 expressions and then add or subtract the root 3 expressions. So if I have 2 root 6 and I take away 5 root 6, if I go 2 minus 5, that's negative 3 root 6. Okay, so that deals with the root 6 expressions, and then if we look at this, we've got positive 7 root 3, and I'm taking away 2 root 3. That would leave us with plus 5 root 3. Okay, so you can leave the answer like that, or you could put the positive expression first, 5 root 3 minus 3 root 6. And you're good to go. We cannot subtract root 3 with root 6 because those are unlike radicals. In part C here, what we have to do first, guys, is make sure that all of our radicals are in simplest radical form. You'll notice that in A and B, we already had simplest radical form. Can't divide out any perfect square factors out of the 5 or the root 6 or the root 3. But in letter C here, we can simplify negative root 27. It is the square root of 9 times the square root of 3. The square root of 5 cannot be broken down, but the square root of 80 can be. The largest perfect square factor that goes into 80 is 16. So I can write it as root 16 times root 5. And finally on the end here I have a minus 2 times the square root of 12. And the square root of 12 can be written as root 4 times root 3. I don't have the coronavirus, I just have this funny cough. All right, so now the next step here, we've got that negative sign. The square root of 9 is 3 times root 3, so we can write 3 root 3 plus 3 root 5. We have minus the square root of 16 is 4, so 4 root 5. And then minus 2 times the square root of 4 is 2, and then times root 3. All right, so we are breaking things down here. This is negative 3 root 3, but notice here, guys, I have 3 root 5s, and I'm taking away 4 root 5s. 3 minus 4 is negative 1, so I could put negative 1 root 5 like this. When it's a 1 out front, or a negative 1, we actually don't write the 1. It's just implied there. And then we have minus 2 times root 3, so that will be minus 4 root 3. And do we have any other like radicals? Yes, we do. Root 3 and root 3. Negative 3 root 3, take away 4 root 3 is minus 7 root 3. minus root 5. And there's our final answer. And now we can get on to multiplying and dividing radicals. Multiplying and dividing radicals follow these formulas. It actually might even be a little bit easier than adding or subtracting. So if you're multiplying mixed radicals, notice you multiply the numbers out front. It goes a times c to give you that. And the square root of b times the square root of d is the square root of b times d. So it's kind of like you multiply the outside numbers and you multiply the inside numbers inside a square root. And with dividing, kind of the same deal. Outside numbers get divided, and then you go the square root of b divided by d. So here's how it looks in practice. Example 4, simplify each of the following expressions. We have negative 3 times the square root of 2x times 4 times the square root of 6. So I'm going to go negative 3 times 4, which is negative 12. And the square root of 2x times the square root of 6, I would go 6 times 2x, which is 12x. And I could write that for starters. And then from there, what you can do is try to simplify what you have inside the brackets, inside the square root. So we have the square root of 12. That can be written as the square root of 4 times the square root of 3. And then we would also have to have the square root of x on the end. And we end up getting negative 12 times the square root of 4 is 2 times the square root of 3 times the square root of x. Negative 12 times 2 is negative 24. And the square root of 3 times the square root of x is the square root of 3x. And that is simplest radical form. In letter B, notice we have a mixed radical multiplied onto a bracket which contains mixed radicals. So we have to do front door bomber. So we're going to bomb that onto that. And when we do that, you multiply the outside numbers. 7 times 5 is 35. The square root of 3 times the square root of 5 is the square root of 15. And then you take the 7 root 3 and you multiply it onto the negative 6 root 3. So 7 times negative 6 is negative 42. The square root of 3 times the square root of 3 is the square root of 9. And see if we can simplify things from there. 15 doesn't have any perfect square factors. The only perfect squares lower than 15 would be 9 and 4, and they don't go in evenly. Minus 42 times the square root of 9 is actually 3. So that simplifies like so. So we end up with 35 root 15 minus 42 times 3, which is 126. And there's our final answer. And finally, example C. In this case, we have a bracket times a bracket, and so we have to do FOIL. So I'm going to do 8 root 2 times 9 root 5. 8 times 9 is 72. Root 2 times root 5 is root 10. And then you do 8 root 2 times 6 root 10. They're both positive, so I'm going to get positive 48 root 20. And then we'll multiply the inside terms. Now the negative 5 doesn't have a root with it, so the negative 5 is just like an outer number. So you go negative 5 times 9, which is negative 45, and then times the root 5. And similarly in the last multiplication, negative 5 times positive 6 is minus 30, and the root 10 is multiplied on as well, like so. And then what do? We collect like radicals. So I have 72 root 10s, and I take away 30 root 10s. That would take me down to 42 root 10s. And then we need to simplify any radicals that we can. The square root of 20 can be written as the square root of 4 times the square root of 5. And we've got minus 45 root 5. Root 5 cannot be broken down anymore, and neither can root 10. So that's why I've left this one. 48 times the square root of 4 is 2. (48 times 2 is 96. And I'm going to collect like terms with those root 5s. So I'm going to go to 42 root 10. And 96 minus 45 is equal to 51 root 5s. We've got root 10, root 5. Those can't be broken down anymore, so this is in simplest radical form. All right, now we can do some division. Example 5, simplify each of the following expressions. And again, you can do outside numbers with outside numbers, inside roots with inside roots. And I just go like this. 8 divided by 2 is 4. The square root of 6 divided by the square root of 3 is the square root of 6 divided by 3, which would just be 2. And root 2 cannot be broken down anymore. So our final answer is 4 root 2. The square root of 80 divided by the square root of 10 is the square root of 8. Just 80 divided by 10. And the square root of 8 can be broken down into the square root of 4 times the square root of 2, which is 2 root 2. So there's simplest radical form. And part C, we have a 2 out front. The square root of 60 divided by the square root of 3 is the square root of 20. And I think to myself, can I break down root 20? Yes, because 4 goes into it, and that's a perfect square. So root 4 times root 5. Square root of 4 is 2. So we end up with 4 root 5. Okay, and we'll finally finish off with something called rationalizing the denominator. And to simplify an expression that has a radical in the denominator, sometimes all we can do is rationalize the denominator. And what that means, guys, is you're basically just making the denominator a rational number. Like, for example, if you have 2 over the square root of 3, the square root of 3 is not a very nice number. It's an irrational number, one where the decimal expansion, it actually doesn't stop, even though it looks like it does on the calculator. It doesn't stop and it doesn't repeat, and this is called an irrational number. And mathematicians, for some reason, don't really like to have irrational numbers on the bottom of a fraction. And so what you do to get rid of the root 3 on the bottom is you just multiply the top and the bottom by whatever was on the denominator. So I have a root 3 on the bottom. I just multiply top and bottom by root 3. It keeps your fraction balanced. It just changes its form. So we end up with 2 root 3 on the top, and the square root of 3 times the square root of 3. At first, it's the square root of 9, but the square root of 9 is just 3. So root 3 times 3 is just 3, and that gives us a nice number in the denominator, which is actually a rational number because you can write it as a fraction, and it gets rid of the square rooty kind of number, which is irrational. And that's what rationalizing the denominator is. Okay, so in these examples, simplify each of the following expressions by rationalizing the denominator. If you have just a single root on the bottom of your fraction, you just multiply top and bottom by that root. And so notice on top we're going to get 4. The square root of 5 times the square root of 3 is the square root of 15. And on the bottom you get 2 times root 3 times root 3 is just 3. And to see that, you would see that it starts off as being root 9. The square root of 9 is just 3, so we end up with 2 times 3 on the bottom. Okay, which is 4 root 15 over 6. And 6 is a nice rational number. So we've rationalized the denominator. The only thing left to do is we could simplify this fraction, 4 over 6, and write it as 2 over 3. And that root 15 is still multiplying on top. So there's our final answer. Okay, now if you don't have just a single term on the bottom, we've got 2 terms, root 5 plus 7. What you have to do to the top and the bottom is you actually have to multiply by something called the conjugate. It's basically the same expression that's on the bottom, you just switch the sign in the middle. So instead of root 5 plus 7, it's root 5 minus 7. Okay, so then on the top we have 11 times root 5, and 11 times negative 7 is minus 77. And on the bottom, root 5 times root 5 is 5. I'm now going to enact the little property that the square root of x times the square root of x just gives us x itself. And notice this, root 5 times negative 7 is minus 7 root 5. And then 7 times root 5 is positive 7 root 5, and those are going to cancel. And then 7 times negative 7 is minus 49. And we'll see that those cancel, so all of my square root expressions are gone from the bottom. The top is 11 root 5 minus 77. And 5 minus 49 is what? Negative 44. Okay, so you can leave it like that, or you can multiply top and bottom by negative 1, and that will switch all the signs of everything, and it'll make a nice positive number on the bottom. It's basically like dividing out a negative 1 out of the top and the bottom, and canceling them. All right, and finally, example C, rationalizing the denominator. We've got 2 terms here, So I'm going to multiply top and bottom by the conjugate, which in this case is going to be 3 root 5 plus 4. 3 root 5 plus 4, like this. This is called the conjugate. Okay, so let's do front door bomber. 2 times 3 root 5 is 6 root 5, and 2 times 4 is plus 8. And on the bottom we have to do FOIL. 3 root 5 times 3 root 5, you go 3 times 3 is 9, times root 5 times root 5 is just going to be 5. 3 root 5 times 4 is positive 12 root 5. And then negative 4 times 3 root 5 is negative 12 root 5. Okay, so you can see that we've got one positive and one negative there, and those are going to cancel. So that's why we have to flip the sign, so that we get that situation happening in the middle of our FOIL. And negative 4 times positive 4 is negative 16, and we can just simplify from here. 12 root 5 take away 12 root 5 cancels. I have 6 root 5 plus 8 on the top. 9 times 5 is 45 minus 16 on the bottom. Root 5 cannot be broken down anymore, but I can go 45 minus 16, which is 29. And that is simplifying by rationalizing the denominator. Okay, so that is lesson 2A, everybody. The homework is actually right here. Please complete the following on a separate sheet of paper. Okay, so there's a good amount of homework there for you, 1 to 6. You can send me an email if you want me to do any videos showing some answers of those. And there are some enrichment exercises in the Pre-Calc 11 textbook. And the Pre-Calc 11 textbook can be found on my website, kamosi.yola site.com. All right, so there you go, everybody. Good luck with the homework. Send me some emails if you need some help, and I will post another lesson next week.